In this video we're going to discuss the notion of direct simplicial approximation. So the context is like this. We've got two abstract simplicial complexes, K and L, and P is going to be a continuous map from the space mod K to the space mod L. So that could be some complicated thing, very wiggly, whatever. And F is going to be a map from the vertices of K to the vertices of L. So that's a nice simple thing, just a map from one finite set to another finite set. We want to define what we mean first to say that F is a direct simplicial approximation for P. So to explain that, let's let X be any point in mod K. And remember then we have a simplex sup X in simp K. So remember X is some convex combination of the vertices of K. And sup X is the set of vertices that have strictly positive coefficient in that expression. And by the definition of mod K, that's got to be a simplex. And then we've got this map P from mod K to mod L and a point X in mod K. So we've got an image PX lying in mod L. And that again, that's a convex combination of the vertices of L. And you look at the vertices that have a strictly positive coefficient. That's called the support of PX. And that's going to be a simplex now of the complex L. There's another thing we can do. We can take this map F that we've got here, a map from the vertices of K to the vertices of L, and we apply it to sup X, which is a subset of vert K, and that gives us a subset of vert L. And as far as we know at the moment, that might be a simplex or it might not be a simplex. And so here's the key definition. We say that F is a direct simplicial approximation for P. If for every point X, as we've got here, then F of the support of X is a subset of the support of PX. And we're going to say that P is directly approximable if an F exists with this property. So now we're going to have a proposition which tells us the key facts about these direct simplicial approximations. The first thing is that if F's a DSA for P, then in fact it's a simplicial morphism from K to L. Remember, that means that it just sends simplices of K to simplices of L. And we already proved a bunch of things about simplicial morphisms. So any simplicial morphism F will give us a homomorphism F lower star from the homology of K to the homology of L. And it will also give us a continuous map mod F from mod K to mod L. So the next claim is that if we look at this map mod F from mod K to mod L, and of course P, the original P, that was also a map from mod K to mod L. So the claim is that those two maps are actually homotopic, even by a straight line homotopy. The third claim is about different simplicial approximations. You see, there might well be two different direct simplicial approximations to the same map P, but it turns out that any two maps like that, they're going to be directly contiguous. Okay. And so by a result that we had a couple of videos ago, if you've got directly contiguous maps, then they give you the same map in homology. So F and G are two different direct simplicial approximations, and F star and G star maps from H star K to H star L, those two maps will be the same. Okay, so let's prove A. Okay, so we're supposed to be proving that F is a simplicial morphism. It's got to send simplices in K to simplices in L. So let's consider a simplex of K, so maybe sigma is V0 up to Vd. And the first point is, well, so F of sigma is supposed to be a simplex, and a simplex has certainly got to be a non-empty set. That's part of basic definitions about simplicial complexes. So let's check that F of sigma is not empty, but that's clear just because F of V0, that's going to be an element of F sigma. So next, let's consider this point X, or otherwise known as sigma hat, which is just the center of the simplex sigma. So we take add up all the V0 up to Vd and divide by d plus 1. That's just the center of the simplex sigma. So that's a point in mod K. And the support is the set of vertices that have positive coefficient. And so those are just the vertices V0 up to Vd plus Vd, which all appear with the coefficient 1 over d plus 1. So we find that the support of X is just the original simplex sigma. And then we've got our point Px lying in mod L, and that's got a support as well, so which we're going to call Tor, so that's some simplex of L. Now the direct simplicial approximation property, as we set up here, that says that f of the support of X has got to be contained in the support of Px. And so here that's saying that f of sigma has to be contained in Tor. So now we're seeing that f sigma, well, it's a non-empty set, and it's a subset of the simplex Tor. And the basic definition about simplicial complexes, if you've got a non-empty subset of a simplex, then it's still a simplex. So we conclude from that that f sigma is actually a simplex of L as required. So that proves our claim B. And now for claim C, so that was claim A. Now we're going to prove claim B. Okay, so we've got some point x in the realization mod k, and again sigma is going to be the support of x, and Tor is going to be the support of px. So sigma is a simplex of k, Tor is a simplex of L. And then the other thing we could do, instead of looking at px, we could take this map mod f and apply that to x. So we've got mod f of x, and want to know what's the support of that. Okay, but if you remember how mod f works, we've got x is a convex combination of vertices, and then we just apply f to those vertices and use the same coefficients. So from that point of view, it's clear that the vertices that you get in mod fx, the support of mod fx, in other words, that's just f of sigma. And the direct simplicial approximation condition tells us that f of sigma is contained in Tor. Okay. So if we look at px and mod fx, they both have support contained in Tor. In other words, these are both points lying in the geometric realization mod Tor. And so it follows that we just draw a straight line from px to mod fx, then that's also going to be contained in this simplex mod Tor, and so it's going to be contained in the realization of L. Okay. And that works for any point x in mod k, and so we can just do a straight line homotopy from p to mod f. So that proves this claim B here. So claim C said that if f and g are two different direct simplicial approximations to the same map P, then they're going to be directly contiguous. So suppose we've got that. So we've got f as before as a direct simplicial approximation, and g is another direct simplicial approximation. Okay. So again, we consider some simplex sigma, and we put x is the center of the realization of sigma, and Tor is the support of px. So as we mentioned in the proof of A, the direct simplicial approximation property for f tells us that f of sigma is contained in Tor. But the direct simplicial approximation property for g tells us that g sigma is contained in Tor. And so if we take the union of those two things, that's still a subset of Tor, and it's still not empty. And by basic fact about simplicial complexes, any non-empty subset of a simplex is a simplex. So we see that f sigma union g sigma is a simplex. And that, by definition, is what it means for f and g to be directly contiguous. That you take f sigma union g sigma, that's supposed to be a simplex for any sigma. And so that's the end of this proof.